มนุษย์เราเริ่มตั้งคำถามเกี่ยวกับกลไกการทำงานพื้นฐานของธรรมชาติมาตั้งแต่ครั้งโบราณกาลองค์ความรู้ที่ได้ถูกส่งต่อจากรุ่นสู่รุ่นถูกพัฒนาปรับเปลี่ยนต่อยอดผ่านการค้นคว้าทดลองตั้งสมมติฐานและพิสูจน์ทางทฤษฎีเพื่อให้เข้าใจถูกต้องมากขึ้นฟิสิกส์ทฤษฎีถือเป็นวิทยาศาสตร์พื้นฐานที่สำคัญอันหนึ่งที่อาศัยแบบจำลองทางคณิตศาสตร์ในการไขความลับความเป็นไปของสิ่งที่อยู่รอบตัวเราตั้งแต่ระดับอะตอมไปจนถึงระดับจักรวาลส่วนหนึ่งของผลสำฤทธิ์ที่มนุษย์ทำความเข้าใจธรรมชาติผ่านภาษาทางคณิตศาสตร์คือเทคโนโลยีอันหลากหลายที่อำนวยความสะดวกในชีวิตประจำวันไม่ว่าจะเป็นโทรศัพท์มือถือคอมพิวเตอร์หรือแม้แต่โครงข่ายอินเทอร์เน็ตที่ทำให้โลกอันกว้างใหญ่แคบลงไปเพียงปลายนิ้วสัมผัสยังมีคำถามอีกมากมายที่เรายังตอบไม่ได้ทั้งหมดเกี่ยวกับธรรมชาติซึ่งถือว่าเป็นเรื่องที่ท้าทายและรอคอยให้นักวิทยาศาสตร์เข้าไปค้นหาคำตอบในอนาคตในปัจจุบันบุคลากรของวิทยาลัยเพื่อการค้นคว้าระดับรากฐานถือได้ว่าเป็นส่วนหนึ่งในการค้นหาคำตอบของคำถามข้างต้นผ่านการทำงานวิจัยหลากหลายที่ให้หัวข้อที่ล้ำหน้า
Okay, good afternoon, everyone, and welcome to IF Colloquium Online Seminar number 2, organized by the Institute for Fundamental Study, No.2 University, Thailand. My name is Kalin Yukong. I am IF Deputy Director of Strategy, and it is a pleasure to welcome everyone to this afternoon online event. Well, first, let me give you the idea of why do we need to do this kind of event. Most of the time, academic conversation would normally circulate among the scientists, yet it's bridging the gap between the science world and the general audiences is very crucial for the country in this current competitive world. Then the Institute for Fundamental Study would like to provide a platform for people who are interested in physics, mathematics, and other related fields come and enjoy in the progress of the advanced research. For this talk number 2, we are very pleased to have Dr. Dalit Samat from Khon University to give us something about exotic hadrons and nuclear forces, actual unsolved problems in standard model. Well, let me spend a little bit more time to introduce our speaker formally. Dr. Dalit Samat received his bachelor degree in physics from Rajapat Institute of Ubon Ratchathani, right? Then he went further for his master's degree in physics at No.2 University, and after that, PhD in physics at Suvarnabhumi University of Technology. At the moment, he is working as a lecturer at Department of Physics, Faculty of Science, Khon University, Thailand. His research interests are something to do with the QCD, I believe, and cosmology, as well as astrophysics. Well, the talk would be roughly 40 minutes long. Before I stop doing the talk, if you have questions, you can send us in the chat box or in the comment. Our staff will collect all the questions and deliver to the speaker at the end. Anyway, without further ado, let me give the skin to our speaker, Dr. Dalit Samat. Well, skin is yours now.
Okay, thank you very much. First of all, I would like to thank the organizer to give me a very good opportunity for giving a talk today. Well, actually, I did have some very deep connection with the IF. Yeah, well, I mean, not first graduate as student of Professor Bruin. So at that moment, it was a TPTP when I study master degree. So yeah, and it is a good, and it's my pleasure to come back online to give a talk here. So yeah, well, today I'm gonna talk about my research idea or my research topic on the hadron physics. Well, but actually I work on several field right now, but my main research is hadron physics. Oh, well, the title is already has been told by Dr. Sikarin, so I won't repeat it here. Oh, well, yeah. By the way, yeah, actually, my talk and all my work about the hadron physics related to the work of the Professor Stephen Weinberg, who passed away recently. Yeah, and I also would like to dedicate my memory to him. Yeah, like you guys see, most of my research topic in hadron physics has some motivation or inspired by the effective field theory in the QCD via the formalism of the Professor Weinberg. Yeah, for example, what I have done so far, chiral perturbation theory is the effective field theory, and chiral Lagrangian method in the nuclear forces, and a so-called Weinberg compositionless condition also has been used in my current work. Yeah. By the way, I also learned a lot of things from his textbook in general relativity. Yeah. So here this is the outline of my talk. So my talk has been decomposed into the 6 part. First we're gonna talk about what is hadron physics, and the second one we have a quick tour of a so-called particle zoo. Yep, and we're gonna continue with the very brief of a so-called quantum chromodynamics, and subsequently we also have a short introduction of a so-called effective field theory in strong interaction, and next we're gonna go to the central part of this talk. I mean the exotic hadron, and next one is also nuclear forces, and I end up with my talk with the conclusion and outlook. All right. Yep. So before we're gonna go to the hadron physics, I would like to remind you guys about what is the nuclear physics and elementary particle physics. So on the left-hand panel, there's a picture is scale of the matter. You see right now up to now, our most accurate theory in physics is a so-called standard model of particle physics. Say that the elementary particle is composed of a quark inside the nucleus, and in addition, there is another kind of matter so-called lepton. For example, is electron surrounded by surrounded atom. Yeah, like you guys see here is if we look closer inside the nucleus of atom, in the nucleus, yeah, everyone know that since I think even middle school, most of us knows already what inside the atom is the so-called nucleus. Nucleus composed of a so-called proton and neutron. Neutral charge is a neutron, and proton is a positive charge. They stick together inside the nucleus, holding by strong force. So for the nuclear physics, they deal with the interaction, composition of particles inside the nucleus, so-called nucleon. I mean, the nucleon is a proton and neutron. Yeah, and then if we look closer, deeper, and we found that there is a so-called set of a so-called elementary particle. So according to the standard model, there are 2 kinds of the particles. First is a fermion. The second one is a boson. Fermion is a matter particle. It means all of the everything we have seen right now, atoms, electrons, and so on, is composed of a fermion. And for the gauge boson is an intermediate or force carrier of the nature. Yeah, for example, photon is a force carrier of electromagnetic force, and for the W, Z, and Z boson is a force carrier for the weak nuclear force, which is force of for beta decay, for example. Yeah, and the gluon is for the force carrier between quarks. Yeah, here is a rough picture of the nucleus. Yeah, we can see when we talk everything about nuclear physics, we just talk about the degree of freedom of the particle inside the nucleus. For example, for the radioactivity, for the nuclear energy fusion and fission, etc. And we're gonna go to see the fundamental particles and interaction in the standard model once again. Yeah, as I mentioned, the fermion is a matter constituent of the nature. Yeah, there's a lepton and quarks. And lepton does not interact with the strong interaction, whereas quarks interact with all kind of the fundamental forces, such as the electromagnetic, because the quarks carry charge. For the weak, they also interact with the WC boson in order to get to make the beta decay possible. I mean, beta decay is a one kind of a radioactivity that can release some energy inside the core of the sun. And most important thing is the quark also interact with a so-called gluon, which is the force carrier of the strong interaction, which is make the quarks stick together to form proton and neutron, etc. Yep. So since we know the rough picture between the nuclear physics and elementary particle physics, so what is a hadron physics? Hadron physics is something like in between nuclear physics and elementary particle physics scale. So we just consider or study or focus on the so-called the particle composed of the quarks and gluons, or we call sometimes we call strongly interacting particles. Yeah, as I mentioned just now, hadron composed of the quarks and interact with the gluons. There are two kinds of the hadron. First, a so-called meson. Meson is composed of quark and antiquark. It forms a so-called integer spin called boson. Spin 1, spin 0, spin 1, etc. And the second kind of the hadron is a baryon. Baryon composed of 3 quarks. So according and quarks carry the spin half quantum number. So for 3 particles, yeah, absolutely, there are two possibilities to form the baryon. Means the first one is a spin half baryon, and second one is spin 3 half baryon, etc. for the excitation state. Yeah, here in the low left-hand picture is the cartoon of the quarks. Yeah, according to our observation right now, there are 6 kinds of quarks, starting from the up quark, down quark, charm quark, stain quark, top quark, and bottom quark. 6 flavor. We call this kind of quantum number is a flavor, and all those kind of flavor different by the mass. The lightest one is a U quark or up quark. The heaviest one is a top quark. Yeah. In addition, we also discriminate the generation of the quarks into 3 classes. First generation is up and down quark. The second generation is a charm quark and strange quark. And the third generation is the top quark and bottom quarks up to now. But maybe some people probably ask, why there is no 4th generation? Well, it might be, or there is some possibility to have the 4th generation of the quarks, but we haven't found it yet. Yeah, and who knows in the future. So, I also want to show you a cartoon of a so-called meson and baryon. Yeah, a meson, you see, for example, this one is a kaon, meson is composed of quark and antiquark, 2 quarks, right? And the baryon, for example, is a proton, also composed of 3 quarks and 2 u quarks and 1 down quark. Yeah. And a so-called deuteron here. Deuteron is a loosely bound state of proton and neutron. Is another isotope of hydrogen. Is a very important particle in order to release energy inside the sun. Well, so I'm gonna go quickly. Yeah, one more thing I would like to tell you guys about the I would say crucial information. Everyone knows that according to the discovery of the Higgs boson, people claim that Higgs boson is a God particle, but like all kind of elementary particle gain mass by the Higgs mechanism. I mean, if the particle move through or pass through a so-called Higgs field, and then they get interaction with the Higgs field, and then they get they're moving slower, and then they gain the mass. Yeah, and people say, okay, we got the mass for all kind of elementary particle, or one may say that the Higgs is a God particle to give the mass for all particles, but all kind of mass we have seen in reality, for example, our sun, our hand, our atom, I would say 99% of the mass came from the atomic nucleus mass. So the atomic nucleus mass composed of a proton and neutron. So the main mechanism of getting mass for the proton and neutron is a so-called chiral condensate. For example, I would like to show you here on this picture. Yeah, normally for the quarks, for example, is for proton. Proton has a mass like about 1 GeV approximately, or 1000 MeV. MeV stands for the mega electron volt. Yeah, for the particle physics people or nuclear physics people, we usually call the mass in the dimension of the energy according to Einstein famous equation, E equal to mc squared, and we set c equal to 1. So mass and particle is this mass and energy is the same thing. Well, for the quarks, average mass of the u and d quark, I mean up and down quark, proton composed of up two up quark and 1 down quark. Each one they have the mass averagely about 3 MeV. So but the proton composed of has a mass about 1000 MeV. So how the other mass come from? I mean, you see, like almost 1,000 times. The mass actually generated from a so-called gluon dynamics. I mean, the dynamics of the quark and gluon inside the proton generate the mass. Mass, as I mentioned just now, mass is equivalent to the energy. So most of the mass of the hadron or the proton or meson or other kind of particles, I mean not elementary one, the composite one, also get the mass from gluon dynamics. And gluon dynamics is the main property of the so-called quantum electrodynamics. And we will see about the quantum chromodynamics in detail in the latter. So what we are studying in the hadron physics right now, so far I just list what is an unsolved problem, or unsolved problem in the hadron physics, which is cannot solve by standard model of particle physics. The first problem is there is no free quark. Yeah, there is no free quark. In the proton, neutron, or other kind of meson, we haven't seen the free quarks. We haven't detected the free quark in the experimental yet. No, because it is because of a so-called confinement mechanism, and I will tell you more about the confinement mechanism in the latter. This is the first one. There is no free quarks. The second one is a so-called mass gap problem, or a so-called mass of hadron problem. As I mentioned, most of the mass of hadron come from the dynamics of gluon, which is can describe by so-called Yang-Mills field. I mean the gauge field, one kind of gauge field, and we cannot solve the Lagrangian of QCD. I mean the Yang-Mills field analytically yet. And if one can solve the Yang-Mills theory in SU3, a flavor of QCD, somebody must get a so-called I cannot remember well the reward of the Clare Mathematics Institute, a so-called like a millennium problem. Yeah, and mass gap of the QCD is one of a millennium problem have been, and this one haven't solved it yet. So if somebody interested to get some money or to get some reward, please go there. Yeah, and another one is a so-called hadronic state. Hadronic state is other hadrons instead of the proton and neutron, what we have seen in the reality in the real world. And but for in the high energy system, we found another kind of the hadron, and there are many kinds of the exotic particles. I mean, not like a meson and baryon, and we're gonna talk about it in a few minutes. All right. In addition, hadronic interaction also is an unsolved problem. So we cannot solve the QCD theory directly to get the interaction between the hadron itself. No, we cannot do it right now. What we have done is make it approximate, calculate it approximately. Yeah, and we cannot use the real theory or to do it. And another one is a so-called spin crisis problem. As probably as we know, proton, for example, proton composed of 3 quarks. According to and the proton holds the spin 1/2. And according to the experimental data, they found that most of the contribution of spin does not come from quarks, come from something else. It is a so-called spin crisis. And I according to time constraint, I won't talk about this in detail. And the last one, according to my knowledge so far, it is a so-called hadronic in matter, like some other hadronic interaction or some properties inside the nuclear matter. And this one can still be the unsolved problem. And we have very rare information data to discover it. Yeah. And this one also leads to a so-called exotic hadron. Exotic nuclei means a nuclei does not compose of the proton and neutron only, and there is another kind of hadron inside the nucleus. Yeah, here is a main research topic in hadron physics, so I'm gonna rush out. Well, yeah, okay. The topic is listed in the slide. So I would like to focus on the so-called nuclear forces from QCD and the exotic hadrons. So which are the main topic in my talk today. And for the other stuff, I will leave for you guys. If you guys interested, you guys can go to check it out later. So before we go to the so-called exotic hadron, I would like to show you what is people collect the data of particle So there are many kinds of particles in the subatomic level. So hadron physics try to classify and manage all kinds of particles in a systematic way, like we do the periodic table of the hadron in like people in chemistry do it. So the information source of this kind of particle is a so-called particle data group. Yeah, and in this website they also provide almost all the thing about almost all the detail of the particle physics. If you guys want to know how many particles we have, how many particles have been discovered, you guys just go to click the particle listing, and you guys will see here is all possible of what we have observed in the lab. Yeah, so I'm gonna focus on the so-called meson and the baryon. You see, there are many kinds of meson, and I will talk about it in detail later. And also for the baryon as well, and you see there are many kinds of the baryon. So what we are going to do in the hadron physics, we try to classify it systematically. So right now, the detail, I won't go into detail. Right now, we have found 315 meson in the lab. Yeah, a lot. Composed of different kind of the quark contents inside. Yeah, and I would like to spread you guys here for the ultralight meson. There are 100 meson state, and another one is a so-called CC bar and BB bar. CC bar means charm and anti-charm quarks, and BB bar means bottom and anti-bottom quark. Yeah. Moreover, for the baryon state also, according to the experimental data and experimental detector, we found that there are currently 176 baryons. A lot. So we still not know the real connection between those kind of baryon or meson. So what we can do right now, we just can make a simple classification, but we would like to do something very clear and in detail, like we have done in the chemistry. So this is the main idea of the hadron physics research. So here is a multiplet of the meson and baryon. As I mentioned, there are two kinds of the traditional meson. Meson is there is a spin 0 and spin 1. Spin 0 we call pseudoscalar particle. We call pseudoscalar because it has a parity transformation odd, not like even. So we call pseudoscalar. Yeah, like a like a meson. Meson composed of two quarks, quarks and antiquark. So those two particles has a spin 1/2, two state of particle 1/2 combined to be the singlet one, spin 0, and the triplet one is a so-called vector meson. The same thing happened like for the 3 quark state, like a baryon. Yeah, 3 spin 1/2 particle, yeah, can be composed into the spin 1/2 and spin 3/2, like this. And this here is a quark content, like a DDD, like a delta minus, and for the proton and neutron, you can see here, proton is a UUD and neutron is a UDD. Yeah. So I'm gonna talk about quantum chromodynamics briefly. So QCD, a so-called quantum chromodynamic can call shortly like QCD. QCD is one part of standard model of particle physics, which is of course, a response for the strong interaction. There are three kinds of the fundamental interaction in the nature, except the gravity, electromagnetic, weak nuclear force, and strong nuclear force, right? As I told you guys just now. So QCD is a local gauge color symmetry. They introduce a so-called color chart called red, green, blue in order to describe the interaction between quarks and gluon. We borrow the idea from the electromagnetic interaction, like for the electric charge and photon, but we extend the symmetry. So here is a cartoon that used to compare the difference between the QCD and QED. You can see like QED is a quantum electrodynamics, is a quantum theory of electrodynamics, electromagnetic force. Yeah, only the charged particle interact with the photon, and that's it. We have only one kind of interaction. But whereas in QCD, yeah, we have the quark and gluon interact each other. Moreover, gluon itself, I mean force carrier, also can interact itself. We call non-abelian gauge boson. Yeah, this makes the QCD more complicated. So yeah, and yeah, of course, QCD is very successful to describe the experimental data, in particular a so-called asymptotic freedom, and this one this result make the people get Nobel Prize in 2006, yeah, if I remember correctly. Yeah, and however, even though the QCD is very precise in the high energy, but at low energy for the nuclear level, according to the coupling constant of the QCD here and the low energy, it becomes bigger and bigger. So we cannot do a so-called perturbative calculation in quantum field theory. And the cutoff scale of the QCD is just about 300 MeV, or it's like a 1 Fermi. Yeah. In addition, color confinement also make the meson and baryon become the colorless. Yeah, that is why we cannot see the free quarks. Most important thing is we still don't have the right connection or complete connection between the high energy one, I mean from QCD, and the low energy one, low energy theory one, I mean some theory of nuclear physics. So we still don't have this good or complete connection yet. This is a very, very crucial problem in the standard model. So I would say there is no good connection between high and low energy, I mean particle physics and nuclear physics. What we can do is just approximate one. So since there is a big gap, Weiberg came up with the idea in 1979 about a so-called effective field theory. What is the main message of his paper? He said one can write down the most general effective Lagrangian up to a given order consistent of all the relevant symmetry of the theory, which is can be used to describe the physics effectively instead of the fundamental theory or underlying theory. So this one can make, if we want to study the QCD, so the effective field theory program is applicable. We have the QCD as a high energy theory. Then we can calculate or we can study the hadronic level by construct the Lagrangian by using the hadron as a elementary degree of freedom instead of quark and gluon directly. However, the most general means there must be infinite number of parameters. I mean, for coupling constant, you can construct all possible. So I'm gonna rush. Yep. Yeah, and it somehow is non-linearizable. And but anyway, we can separate into the low energy, and then we can make a systematic expansion instead of coupling constant. And another one is a so-called Weisberg condition. Also, I would like to give you a very short. So Weisberg composite condition used to describe the molecular structure of the hadron. For example, the most important example is a deuteron. Deuteron is a bound state of proton and neutron. It forms like a loosely bound state between proton and neutron. Deuteron. One can think like it is one kind of hadron and molecular state of the hadron with some binding energy. So Weisberg composite condition is just say that the wave function renormalization of the molecular state must be equal to 0. Yeah, and then we got the molecular structure. And so we come to a so-called exotic hadron. So as I mentioned earlier, for the conventional hadrons, we have the quark anti-quark as a meson and 3 quark as a baryon. And in addition, we also have a bound state of the proton and neutron, and so-called deuteron. But in experimental evidence, we have found a huge number of exotic states. So one might say like a hybrid. Hybrid means like a gluon mixed up with the quarks, or the hadron made of gluon itself only. Another kind of exotic hadron is so-called traitor quark, means there are 2 pairs of quark and antiquark. And another one is a pentaquark. Pentaquark means 1 baryon and 1 meson stay together inside the 1 hadron, so it forms like a pentaquark. And another kind is a hadronic molecule, etc. What we call exotic means the quantum number does not fit with the conventional hadrons. All right. So yeah, there are many theoretical approaches to explain the exotic hadron. So I would like to focus on the hadronic molecule. No, I don't think I have time. So okay, anyway. So let me move. I think yeah, this is a list of the theoretical approach for the exotic hadron. So let me move to the so-called another interesting exotic hadrons, so-called XYZ. Like you people might see from the news, for the scientific news, oh, in the CERN we have found a new particle, in other lab we have seen new particles, blah, 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 blah. So those kind of particle is somehow a so-called XYZ particle. It like a charmonium. It looks like a charmonium. Charmonium means a bound state between charm and anti-charm quark. We call charmonium. Yeah, it has been detected a lot in the experimental lab, and mainly this discovery came from the B meson decays. Yeah, XYZ state or exotic hadron cannot use the standard model of the QCD to explain the structure. So let me introduce you about a so-called X particle. X particle is a state like a came from CC bar decay. We call the X particle. For the Y particle also came from the CC bar, but the main channel came from the electron-positron annihilation with the isospin singlet. And for the C particle, it has a charge and carry the spin triplet. isospin triplet, sorry. Yeah, and for the C is also has a charge. Yeah, is the difference between those XYZ particles. According to the Wikipedia, I just copy from the Wikipedia. They don't update the very recent discovery of the new particle yet. That one is a C particle. Yeah. Up to now, since here is the list of discovery of the exotic particles. It might be the tracer quark, or it might be molecular state. Still, we don't know it yet. But since after 2012, since the discovery of the Higgs boson, there are 62 exotic hadron discovered at CERN. Yeah, you guys can see from the graph. Up to now, up to this year, there are 62 exotic particles. So here are my works on exotic hadron. I use a Weisberg approach about the effective field theory to describe the resonance of the charm baryon and Pendel quark. Yeah, and I also use a quark model to calculate the property of X particle 1875, and we claim that is a nucleon and anti-nucleon bound state. And currently, I work with the people in UK about the so-called D star 2380 is a spin 3 particle. With the people, experiment people from the University of York in UK, and we are doing it now, and we try to explore more about its property. We want to show it is whether 6 quark state or molecular state. So the last part, I mean, for the nuclear force from QCD, I think I should not have more time. I would say shortly, nuclear force from the QCD. Everyone know that Yukawa sensei have shown that the nuclear force, I mean the force that hold the proton and proton or proton neutron to stay together inside the nucleus, came from the so-called pion exchange force. But pion and nucleon also one part of the particle in the QCD, I mean the composite particles from the quarks and gluons. So one may call that a nuclear force is a residual force from the QCD interaction. And we still don't have the good connection between the phenomenological potential that used to describe pion-pion interaction in the nucleon scattering yet. Here is another strange another nuclear chart with the strangeness. With strangeness means that we have additional S quark inside the nucleus. Yeah, still cannot describe by the QCD directly. So we're gonna use the same terminology of the Weisberg effective field theory to construct a so-called effective field or effective theory of nuclear force. Yeah, and the process, it can be like we just identify the high energy theory, which means the fundamental theory is a QCD, and we consider or we focus on the very low energy level, and then we identify the scale of the physics there, and then we make a expansion as a ratio of the energy scale that we interest with the cutoff. Here is a hierarchy of the nuclear force in the chiral effective field theory. Yeah, so we use the chiral effective, we use the chiral symmetry. I mean the symmetry of U quark, D quark, S quark as we consider it as a massless, so it becomes a chiral symmetry, and we use this symmetry is very good symmetry to study nuclear physics in the low energy. Yeah, and this we just make it systematically to calculate it, and up to now they try to reproduce up to the carbon 12 already by using the effective field theory, but it is very tedious calculation. But we still need to find more accurate method to do this. So yeah, I just skip this one. So my work on the nuclear forces by using the large NC. I mean, large NC is one kind of approximation that we extend the number of color from 3 into the large number, make it systematically expansion, and eventually cut like a next to leading order, and then set NC equal to 3 and find some scaling of the parameters. And yeah, I combine a so-called large NC and chiral effective field theory to constrain the coupling constant of SU3 flavor symmetry baryon interaction from the chiral effective Lagrangian. In addition, I also use a large NC to apply to the see why there is no pion exchange in the so-called parity violation of the nucleon scattering. And finally, I also use large NC to constrain the size of the nuclear force in the time reversal violation in the nucleon scattering as well. So I'm gonna finish my talk and the conclusion and outlook. Yeah, even though the standard model is very successful theory to this kind of elementary particle and its interaction, but the QCD, I mean, a part of the standard model suffer with a lot of problem at low energies. A rich spectrum of the hadron cannot describe by QCD directly, as well as the nuclear force. The effective field theory and other non-perturbative approach might be help to understand or fix the problem of the standard model, but seems to me we need a new paradigm. Maybe standard model is not very complete, but yeah, we just keep playing the jigsaw, input more some unclear feature or unclear solution of the standard model. Yeah, and I think my time is gone. So thank you for your attention, and I would like to announce something or advertise my research group. Yeah, in Khon University. In Khon University, at Khon University, we are a very small group that we work on the high energy physics, nuclear physics, astrophysics, and cosmology. And another, we have 2 lecturers. One is my colleague, Professor Shakrit, and I myself. So if you guys interested on doing this kind of research, please contact us by searching the Google on this name. So thank you for your attention. Yep. Sorry, I cannot tell you guys all the detail. Yeah.
Well, okay, that is okay. I think because this kind of topic is very huge, right? I mean, well, you might need more time for telling us about the whole story. But anyway, well, thank you very much for this kind of wonderful overview talk on particle physics, especially on the hadron physics, right? Yeah, very interesting. Yeah. And well, you could see from the message from the Facebook page that you get a lot of cheerful message here from your colleagues and your friends here.
And actually, it's kind of like it's kind of like in conspiracy one, I guess.
Well, anyway.
I sorry. Thanks you guys for sharing up me, but I didn't have time to look at the message.
Oh, yeah. Well, yeah. Well, you can look at that later. Yeah, you will see a lot of very cheerful messages from your friends and your colleagues. So anyway, So, well, let me ask you some few more questions. So, well, it seems to me that there is still, well, a lot of room for people to get into this kind of research field, right? Because there is a huge number of unsolved problems that you mentioned, right?
Yep.
Well, in this kind of standard model, and you also mentioned that actually a standard model is not, maybe it's not the final theory to explain the nature, right? We seem to me that
No,
we
it's
need
not
some,
complete yet. It's not complete
yeah,
yet.
we need new kind of physics, right?
Yeah.
And well,
See.
the question is, in your opinion, what kind of physics that, well, what kind of new physics that do we need to in our which direction that we should go, right? String theory or
Oh,
supersymmetry or
well, I don't think so. I still, well, even I have a lot of the colleagues who are the people in the beyond standard model stuff. They are very happy with the successful of standard model. But I think well, for the new physics, so-called for new physics, I think we must rethink about the problem of the problem of the model itself. I mean, for in particular, I would say for the gauge field theory of the standard model, I think we still miss something. We don't know yet if we know that the problem could be solved, but I think we don't need to go to very high energy like a supersymmetry
okay.
Or the string theory stuff like that. Even I work on this kind of topic also, my colleague, but I think, and my former supervisor also think, and most of the people in in the head-on physics community think we still need to find more property of the for the QCD Lagrangian itself. I think we don't need to go, but we need some another clever idea to fulfill. We still close to solve it, but
Okay.
something.
So, well, it seemed to me that you mean that we kind of you try to decorate your Lagrangian in some way, right? To make it fit to the experimental result somehow. Is that right? Right. So it means that we don't need some kind of very fancy theory. More fair. Well, I mean, what I mean by fancy, like a string or supersymmetry, right?
No, we don't need.
Yeah. All right. Okay.
But I also work on this kind of thing.
right.
But to get play with it, to see what are people in other fields think, and but maybe, but for me,
well, the thing is that the people who working on this kind of your colleague actually that working on this kind of thing theory or supersymmetry will maybe get upset when they heard this kind of that you don't agree with that what they are working is kind of the maybe to give up the final answer. Well, anyway. So well, anyway, there is a question from the audience. Actually, let me go for the first one. Where most of the mass of the proton come from? Is that from the strong interaction?
This is it's a dynamics or a so-called QCD vacuum. I mean that as I mentioned, right? Maybe I spoke too fast because according to time constraints. So I would like to repeat it once again clearly.
Okay.
So normally the quark and the gluon, they stick together, right? I mean they have an interaction. I mean exchange quark gluons, exchange each other, and then so during the exchange process, the gluon field also fluctuate according to the Heisenberg uncertainty principle. So fluctuate a lot, and the outcome of the QCD also give the mass. I would say it is the mass comes from the dynamics of the quark and gluon interaction inside the proton. I would say, yeah, for the rough picture.
Okay.
Yeah.
So with the follow-up from this question, that actually you mentioned in your talk about the mass on and also the Higgs boson, right? Actually, the mass, the Higgs boson and the Higgs field is kind of responsibility for the mass for the elementary particles, right?
Exactly.
Not for our body mass, something like that.
No,
right?
not for the mass inside the nucleus.
Yeah.
Which is
Okay.
90% of the mass of atom. So
All right. Okay.
Higgs do nothing with us.
Yeah. All right. That's a good point because
in the nuclear level. Yeah.
Yeah, because normally people outside the physics field or this kind of particle physics might be misunderstood about this kind of Higgs particle, mass over mass body, something like that, right? Yeah. This is very good point that you mentioned this.
Yeah.
Okay, there is another more question. The second one from in your work you use big N equal to 3 as a good expansion parameter. Do you have any opinion for N equal to 2 as being a good parameter, expansion parameter? After all, alpha S approximately 0.1 imply 1 over N equal to 1 as a kind of expansion? Well, this is very technical question. Well, do you get it?
I probably know why the people ask like this. Normally we know, right? The number of the color is a 3, red, green, blue, or whatever people like to call, but there are 3 degrees of freedom. So to make the 1 over NC expansion works, I mean in reality, we finally end up with an NC equal to 3, but this kind of approach is like we expand the sum observable up to 1 over NC square at least to make it predictable. For sure, 1 over third is 1/3 is a sorry to say it's bullshit, but but 1 to NC square that I think that to me that's a fine. So if you want to gain more information, you need good muscle to do more calculation, and you can get more accurate the result. But I would say naively or superficially, this kind of expansion or approximation, it looks like not good or unreliable, but we knew this limitation. But if we follow the way or the method or the approach, and then we start we start the calculation up to 1 over NC, I mean the second order, you see, the second order one that would provide something. And at least in my previous work, we span up to the 1 over NC to the third to see why there is no pion exchange in the nucleon interaction for the parity violation. You see, like for to 1 over NC square, okay, we still see some effect. But if we expand more, even it's a 1 over 27, right? It's quite a good number, no? Is it? We can see more digits, and we can and the prediction is very fit with the experimental data. So up to now, I would say up to now, it's not the only one approximation that can use, but it something like it is an auxiliary method or approximation to fulfill with other non-perturbative approach.
Okay. All right. Okay. All right. Okay. there is another question, right? Okay, from the online audience. Can you make some comment on ADS QCD? Can you?
It's a
I
funny
don't.
way to do the calculation. Yeah. For the people who love string theory, and well, actually, it is a very ADS QCD is another kind of the approximation from a so-called the ADS CFT, right? CFT is a conformal field theory in 4 dimensions.
Yeah.
Yeah, conformal field theory in the exact limit of the QCD. QCD is not the conformal field theory, but for the large n limit, it is equivalent, and it's another kind of the way to do calculation and to see maybe people have some convincing result to they reproduce a lot of result like the heavy ion collision or quark-gluon plasma, stuff like that. Like the picture we can see on the 4 dimension, it somehow is a mapping of the physics of the black hole in 5-dimensional space-time. And okay, we find some correct the parameter 1 or 2, but I think it is a good way, but it's a good way to fulfill what we lack. But I don't think it's a final one.
All right. Okay.
I still be very optimistic, but at the same time, I also skeptical. But it is the way to do it. But
Okay.
anyway, yeah.
Okay.
It's a,
Well.
yeah.
Well, I think it's just good to be optimistic. Well,
Right.
otherwise, then well, we stop asking question, right? Then yeah, that well. Anyway, that is just one comment from a guy from Philippines that asking for like possible collaboration with you, but you can look by yourself after the talk in the comment of the live here. Anyway, one more thing. I think you mentioned about Yang-Mills mass gap problem, right?
Yep.
And then as you mentioned that this is like a millennium problem.
Problem.
Yep. Yeah. Can you give us a little bit more why it's so difficult to solve, make it well?
I
don't know
in the detail correctly, but according to the symmetry SU3 on local one, we cannot solve the dynamical equation of Yang-Mills theory.
Right. Okay.
At the SU3 gauge group. I don't know in the detail, but what we can do right now, we can use the so-called approximation by using computer. That this method leads to a so-called lattice QCD calculation.
All right. Okay.
And what we can do now, just like that, according to the big cupping constant. Yeah, like we do it in the quantum mechanics or the quantum field theory, right? We need to find some small parameter in order to make a so-called expansion to calculate like that in the Dyson series, stuff like that. I mean, in technically, we need to find another non-approximation like that. We calculate the scattering amplitude without using Dyson series. How can you do it? How can you do it?
All right, that's good. That is a good question. Right?
Yeah. So we don't know how to do it.
Yeah. You mean this theory it's not perturbative, right? It's
no, kind of it's non-perturbative in the low energy, but you can work on the perturbative one at a very high energy, because the coupling constant of QCD it's like asymptotic freedom, right? It's in the very high energy, it becomes low and low. So since the coupling is low, we can do the perturbative expansion like in QED, right? QED is the phi structure is 1/137.
Okay.
Right. So we can do expansion as much as we like. But QCD is another story.
All right. Okay. Interesting. Well, I think the for the people who are interested in this kind of millennium problem can Google it in more
Integrable
detail.
system might be helpful, I guess.
Well, possibly, I don't know. Well, I have no idea actually.
Me too. But in order to crack, to calculate, to find the exact solution of the dynamic
Well,
problem.
oh, yeah, indeed. Okay. Oh, let me comment one more thing about, you mentioned about discovery of the new particle, which is actually made of like a four quarks, right?
Yeah.
But you actually you mentioned that there is nothing to be excited with this kind of this discovery,
Well,
because this gave us nothing new, right?
cannot say nothing new, but it's a picture that we know. But since we discover more, it means
Alright,
we
okay.
get more information
All right,
to
okay.
circumstand what we don't know in the QCD.
All right, okay.
It okay, naively, since we are researcher, discover new data. It means we have a new work to do.
All right, okay.
But I don't want to say like it's a nothing new, but
Okay.
it's a picture. I mean, like we get more piece of jigsaw.
I see.
We get new. It's also very important indeed.
All
but
right.
but people, somebody might feel nothing, because people it's just like a full quark, but how can you calculate this if another people?
All right.
So
Okay.
it make us gain more information. It's also exciting, but not like we discover new physics.
Okay.
Yeah, but we get more useful information, I would say. Yeah, cannot be happy too much, but cannot be neutral. In the middle way,
Okay.
like a so-called head-on physics. It's not nuclear physics or it's not elementary particle. It's in middle, in between.
All right. Okay. Okay. And then, let me ask you in this way: what kind of discovery that could make you excited about? Well, I mean, in terms of the particle physics, or I don't know.
We find new way to get the exact solution of Yang-Mills theory.
All right. Okay. Okay. That's right. Okay.
Like you guys can solve a Navier-Stokes equation, right? Or you guys can solve the Ising model in 3 dimensions. Exactly the same.
All right. Okay.
Exactly the same.
Well, that are all the same level of difficulty, right? I think. Okay. All right. Okay. I think it's about the time. Okay. I think I would like to thank our speaker again, Dr. Daris Samad, right, for this kind of very wonderful talk, kind of in the about this hadron physics. Okay. And thank you. I would like also to thank everyone to stay with us here online about hour. Yeah. Okay. Before we go, please don't forget to complete the survey form for us in the chat box. You can go for that, and you could help us to improve our activity in the future. If you have comments or suggestions or topics that you would like to listen about, for the like a frontier physics, or what kind of what branch of research that you are interested in, that we can look at that, and if we have chance we could organize that for you. All right, and anyway, thank you again, and see you again next month for if Colloquium number 3 on the topic, I think, dark matter. Okay, stay tuned. Bye for now. Anyway, thank you very much. Bye bye.
Thank you very much, guys. Bye bye.